In this presentation, we will explain the history, function, and application of dynamometers and how they relate to ME 333. A dynamometer, also known as a dyno, is most commonly used by automotive companies and hobbyists alike to monitor, track, and optimize engine performance for a specific application. Two of the most common methods of engine monitoring are the chassis dyno and the engine dyno. The chassis dyno is most commonly used in recreational setting due to its easy setup. The driver parks his or her car on a platform and parks the drive wheels on large rollers. The car is then secured with straps attached to its frame and fastened to a secure mount. The car is then run through a variety of engine speeds, and a computer displays the engine torque and horsepower curves. The engine dyno test is similar to the chassis dyno. However, in this case, the engine is separate from the car and is attached directly to the dynamometer. This application is used for serious tuning and performance motorsports due to its high level of accuracy and difficulty of setup. The engine dyno is closest to the true horsepower output of the engine.
In 1719, the first dyno was invented as a way to measure human strength. Then, in 1821, the pony brake dyno was invented as a way to measure work using weight and friction. It wasn't until 1928 that the first automobile dyno was invented. Then, in 1931, the eddy current dyno was invented. This is the most common type of dyno found today and will be discussed in greater detail later in the presentation.
There are many types of dynos which can be classified by their braking type. Braking is how the rotation of the crankshaft is resisted to measure the engine's power. In the interest of time, we will describe a few of these different types and how they resist the rotation of the crankshaft.
A water dyno is resisted when a paddle driven by the engine motion spins through water, which can be pumped at various speeds for different levels of resistance.
A hydraulic dyno is controlled by a hydraulic pump, which is driven by the engine motion. The outflow nozzles open and closed at various diameters to provide different levels of resistance. A hysteresis dyno is controlled by a steel rotor which is spun through a variable magnetic field. Electromagnets resist the rotation with respect to the strength of the field.
An oil shear dyno transmits torque by having oil between a brake and a rotor. The torque and power are measured from a variable clamping pressure between this brake and rotor.
Here is a setup for a simple eddy current engine dyno. A spinning rotor, which is powered by the engine being tested, passes in between stators, which transduces the rotational energy into electrical power. The electrical power is then conditioned so that a computer and a DAC can accept the signal. Computer software interprets this signal and displays the engine power and torque as a useful numeric output. This numeric output is determined by governing equations which are fossilized in the computer software, which is unique to every dyno. Some sources of error which need to be considered when operating a dyno include the following. Stator restriction and mechanical stator imbalance are caused by wear, corrosion, and high temperatures, which result in a greater variance of the output. Windage losses, which are losses due to the spinning rotor, and trunnion bearing errors are introduced through rotational friction. These reduce the effective engine output seen by the dyno if not accounted for. Dimensional error is error which scales with the power output of the engine. For example, a 10 horsepower engine, when dynoed, might show a range of 9.9 to 10.1 horsepower, whereas a 1,000 horsepower engine might show a range of 950 to 1,050 horsepower. There can be errors with the construction and implementation of the torque indicator and load cell. The environmental conditions of the test cell will also greatly impact the performance of the engine being tested. These conditions need to be documented in order for the results to be meaningful.
To calibrate a dyno, an operator installs a calibration arm of a known length and weight and adds additional weights to the arm. The resulting torque can be compared to the dyno output to test its accuracy.
Indicated power describes the expected power that would be produced from the expansion of the fuel and air in the cylinder. The brake power is the actual power delivered to the crankshaft of the engine. Knowing these two values allows the owner to know the overall losses of the engine from heat loss, electrical accessories, and friction. Using the torque and power curves from a dyno test, an owner can adjust the location and magnitude of the peaks through various tuning options, allowing peak performance for a desired application. On the bottom of the picture, you can see the operating conditions of the test.